We're continuing the second part of the video on rotational motion, energy, and momentum. So we just did an example where we calculated the rotational kinetic energy. We'll do another example now. So what is the rotational kinetic energy of the Earth spinning around its axis? So just because of its rotation, just the fact that it's spinning around an axis, how much energy is there simply because of that motion? So, okay, so again, we get to use our formula, K equals 1/2 I omega squared. Now we need we need I and we need omega. So I is, well, we have a sphere, a solid sphere in fact, and the moment of inertia for a solid sphere is 2/5 mr squared. M here is the mass of the Earth, and r here is the radius of the Earth. The Earth's not a perfect sphere, but we're going to assume it is. It's going to be close enough. Right, so now we do have to look up the numbers here for the mass of the Earth and the mass of the radius. Excuse me, the mass of the Earth and the radius of the Earth. And those end up being these two numbers, as you see, giving a final moment of inertia of just a little bit less than, well, 10 times 10 to the 37, 10 to the 38 kilogram meters squared. So that's the moment of inertia of the Earth around its central axis. Okay, now we need omega as well. So, well, again, I think what we know is, what all of us know without having to look anything up, is the period. We know how long it takes for the Earth to rotate one time, and that's 24 hours, yeah, right? One day. 24 hours is 86,400 seconds, right? And so then, as we did on the previous problem, to get our omega, we're going to take 1 over that, which actually just that is the frequency. That would be hertz. And then we are going to multiply by 2 pi radians. 5.43 times 10 to the 5th radians per second. So that's the angular velocity of the Earth as it spins around its axis. All right, so now we're ready to put everything into the kinetic energy formula. So we just plug everything as it is. Here's the I, here's the omega. Don't forget to square the omega, giving you final answer of 1.43 times 10 to the 49 joules of energy. So a lot of kinetic energy from the Earth spinning on its axis. This is not taking into account the Earth revolving around the Sun. Of course, that would be additional energy from that point of view. Okay. Next, we're going to switch to momentum and how momentum figures into rotational motion. So, of course, regular momentum was P equals mv, the mass times the velocity. Now, we're not going to use that directly in rotational motion, so we're going to go back to sort of an analogous thing. Instead of actually having true momentum, we're going to have a rotational version of momentum. And it's called angular momentum. We use the letter L, and I won't go into the details of why. Well, actually I will in just a second, kind of give you a reason why, but I won't show you the math behind it. Again, you know, M, replace M with I, and replace V with omega, and see if that works. And it turns out that that does work as a useful thing. So that's what we call angular momentum. Again, the symbol we use is an L, a capital L, and it's just equal to I times omega. That is the angular momentum of an object rotating around an axis. Now, I will say briefly, without getting into too much detail, that momentum, remember, was really a vector, because V is really a vector. And so P equals mv was really a vector equation. And angular momentum also can be thought of as a vector. now we don't have to when we just have an object that's rotating around an axis, because remember, when an object rotates around an axis, it's pretty much it's akin to a 1D situation, because there's only two directions you can go, clockwise and counterclockwise, plus or minus. So you don't have to have vectors for that. But when you're talking about full-blown 3D spatial relationships, it does turn out to be useful to talk about angular momentum as a vector. And so if I drew a picture, and to make it simple, let me draw a sphere for my object. And let's say that this thing is rotating around this way, around an axis that goes right through the middle, right? So this is the axis, and it's spinning around. So actually, L itself as a vector, again, this is going to be its magnitude. That's the right formula for the magnitude. But then the question is, what direction does the L vector point? And the L vector points along the axis. It points along the axis, which is weird. So yeah, it points along the axis. If I drew a disk, so we're looking straight down at the flat disk, and if it were rotating this way, then actually the axis is coming out at you from the screen, right? L is coming right out at you from this dot. So we need that third dimension to picture it. And so the L vector would actually be coming right out of you, right out of the screen at you from that point. So it's kind of hard to draw in this flattened 2D picture, but it'll be coming right at you. In this attempt at a 3D picture, you can see it. So now, how do you know it's pointing, in this case, how do you know it's pointing up and not down? Because both of those would be along the axis. Well, you use what's called the right-hand rule. And in physics, there's a number of right-hand rules. We're going to learn other right-hand rules next semester in electricity and magnetism, particularly with magnetism. And I'm going to have to show you this in class, but if you take your right hand, and it has to be your right hand for this to work, and you know how, ignore your thumb for just a second, you can kind of like curl your fingers in sort of a, like as if your fingers were like around a cup, around a mug, right? Your fingers can curl. Now arrange your right hand so that your fingers are curling in the way that this is rotating. And if you do that, now stick your thumb straight out, as like off of your hand. Your thumb will point up this way, not down this way. And the right hand rule is that L goes in the direction that your thumb points. So again, in this picture, if you cup or curl your fingers in a way that is in the way that this disk is rotating, you'll find, so around this way, you'll find that your thumb is pointing back at you, so it's coming out, right? It could have been going in, could have been going into the screen or away from you, but no, when it's going this way, your thumb is pointing back at you, back out of the screen, that direction. If it was going clockwise, you'd have to turn your hand around and your thumb would be pointing the other way. So anyway, that's the convention for L, and it just turns out like all the formulas are set up so that that direction of L is assumed to be true. So that's the vector version of L. Now I've already spent more time on this than I wanted to, but we might talk about the vector part of L right at the end of this chapter of this set of videos. Okay, but again, for now we won't worry about L as a vector. We won't worry about the direction of L, but this is its quantity. Now, the reason L is defined this way is because just as we had F equals ma could be rewritten as F was the derivative of regular momentum, P, it turns out that net torque is the derivative of angular momentum, if this is how you define angular momentum. So that's why this is the choice for what angular momentum is supposed to be. So this is the second law rotational version, but now in terms of angular momentum. And I don't know that we'll actually use this in any problems. We could get into a set of problems that use this, and we could talk about like impulse and momentum and that approach, like we did for force. We could do rotational versions of those, but we're not going to do that. So I'm just pointing this out just sort of for completeness, but I don't know that we'll actually use this directly. I don't think so. But the thing I do want to, and I guess it does use that equation, but only tangentially. What I really want to talk about is the conservation law that goes with it. So we had conservation of regular momentum, and that was an important thing, and we used it with collisions and things like that. Well, for the same reason, so torque, the net torque is the derivative of angular momentum. So if you believe that, if you start there, now if we have no net external torque, if there's no net torque, right, then this will be 0. And so you have dl dt equals 0. Well, something whose derivative is 0 is constant, so you get L as a constant. And that can be useful, just like conservation of regular momentum was useful. So this is the conservation of angular momentum law. If no net external torque acts on an object or a system, then the total angular momentum remains constant. Now remember that L is I alpha, and so I want to direct you to this picture, which we've all seen ice skaters do, where they start spinning, and they're spinning around and around, and then they bring their arms in toward their bodies, and that causes them to spin faster. Now what's the physics behind that? Well, what's going on here is they're a self-contained system. They're on ice, so let's assume there's little or no friction. So there's no external force, so therefore there's definitely no external torque. And so their angular momentum has to stay constant. So the before angular momentum has to equal the final angular momentum. So L is I times alpha. So the initial I times alpha has to equal their final I times alpha. It has to be the same. What's going on is when their arms are out, that means their mass, some of their mass at least, is out further away with bigger R. Remember, this is their axis. When their arm is all the way out here, right, then that's a bigger R. That's further away. So some of their mass is further away, and if you remember, I is based on an mr squared kind of formula. So when your mass is further away, you're going to have more I. You're going to have a bigger I. So this was bigger. But when they pull their arms in, then the R gets smaller. It's the same amount of M, right, but smaller R. And so they will have a smaller I. Right? But overall, these two sides have to equal. So if the I is getting smaller as you go from initial to final, the compensation has to be that alpha must be getting bigger. So whereas maybe this alpha originally was not too big, it's going to have to get bigger, right, to make up for the smaller I that it's multiplying with. So that's the idea. So conservation of angular momentum explains why a skater will spin faster when he or she brings their arms inward. I'll do a quick example, a different kind of example using this idea, and then we'll stop this part of the video and then have another part. Okay, so a disk of radius 0.25 meters with a mass of 0.35 kilograms is spinning with an angular velocity of 8.5 radians per second. So let's say it's spinning counterclockwise. There we go. Now, a second disk of radius 0.15 meters, so a smaller one, and mass 0.20 kilograms, so a little bit lighter, is dropped on top of it. And I didn't say it in the description, but let's assume it's sort of concentric, like it's right on, the centers are on top of each other. So like from a side-on point of view, what we're looking at here is we've got the first disk, and then we've got the second disk right on top. And the second guy was not rotating when we dropped it on top, but eventually, because of some friction between them, they will start rotating together, and they will start like maybe at first there'll be some slippage between them, but eventually they'll come together and they'll rotate as one. Friction will keep them rotating together. So how fast will it be rotating after all that has happened? I mean, essentially, this is a rotational version of a collision. So what we can do is use Li equals Lf. Angular momentum beforehand equals angular momentum afterward. So we have disk number 1 and disk number 2. So we'll have I1 omega 1I plus I2 omega 2I, and then equals. So actually, let me talk about this. So unlike the skater, with the skater, she actually changed her geometry by pulling her arms in, so her eye changed. But these disks are not going to change their shape or their size, so the eye is staying the same on both sides. So I'm not putting I1I, I'm just putting I1. There's not going to be an I and an F for the moment of inertia. So I1 and I2 times their initial angular velocities. Of course, this guy right here is 0, because the second disk that we drop on at first is not rotating. Okay, and that's going to equal their final angular momentum. So I1 omega f plus I2 omega f. And in this case, omega f, I don't need a 1 and a 2 on them because they're going to rotate together, so they're going to have the same omega f. So I don't need to, it's the same number here and here. And that's what I want, right? I want to solve for that omega f. In fact, I can right off the bat factor it out because it's common, and then that's what I'm going to solve for. So this is what I'm looking at. I solve for omega f. It's going to be I1 omega 1 I over I1 plus I2. So I'm using conservation of angular momentum to figure out this final angular velocity. Okay, now I do have to figure out the individual I's. We're talking about disks, so I'm talking about, and they're solid disks. 1/2 mr squared is the operating formula for that situation. So let me just get that down on the screen real quick. Okay, so you just plug in the m's and the r's for these guys, and those are the numbers you'll get. All right, and so now we can complete this calculation. There's all the numbers plugged in, and we end up getting 7.05 radians per second. So of course it's less than it was going. It was going 8.5. I should only have two significant figures here, so let's just call it 7.1. 7.1 radians per second. Yeah, so a little bit slower because it had to get the other guy moving a little bit, get the second disk moving. It had to give up some of its speed. Okay, so there's an example of using conservation of angular momentum. Okay, so what I want to now switch to is, again, up till now we've been focusing on an object that was kind of pinned in one place. It was not going to move anywhere, and it had a fixed axis, and it could rotate around that axis, but again, it wasn't moving anywhere. But let's just temporarily, or just for a little bit, think about a more general situation where an object maybe is free to move and to rotate. Okay, so well, from an energy point of view, and I mentioned this earlier, you have two parts to your kinetic energy now. You have what we'll call the translational. Translational is a fancy word for like regular motion, like moving from one point to another. Like the whole object, the whole system is just moving from one point to another. And based on its speed, that's its kinetic energy. So that's the old original kinetic energy that we're used to. And now, but if it was also rotating while it moved, it's going to also have rotational kinetic energy. And the two of them have to be added together to give the overall kinetic energy. Okay. Now, what's the story on force? So when a force acts on an object, it's kind of double duty. It can do two things. First of all, it's a force, and so through F equals ma, it will contribute to acceleration, right? It will work into F equals ma, and that'll be the center of mass is like the point. We're going to pretend that all the mass is at that one point called the center of mass, and that's the point that accelerates. But then also, at the same time, like I said, double duty, the force may also be a torque. And so where the center of mass, you can use the center of mass as the axis of rotation, and there'll be a torque, and so it may accelerate in an angular sense. So in other words, let's say we have some irregular object, and it's not fixed anywhere. But let's say it has a center of mass somewhere right in here, right? So now if we, give it a push with a force, then first of all, this thing is going to accelerate this way. It doesn't matter that for that part of it, it doesn't matter that we were pushing up here or in the middle or down here. It doesn't matter. We talked before about how all the external forces, you can just pretend as if they were all acting at the center of mass. So this thing will accelerate, and it will move, and in particular the center of mass will move, so it'll get faster, depending on how long we apply the force for, and the center of mass will now be over here. However, the double duty part of it is this is also going to create a torque, because there's the point of application, right? So if I draw the line from the center of mass to that point of application, this force isn't perfectly perpendicular to that line, but a piece of it is. We can break it down into a parallel piece and a perpendicular piece, and this perpendicular piece exists, and here's the R, and so there's going to be a torque. So there's going to be a torque of F perp times R, and that's going to make it turn clockwise. So there's going to be an angular acceleration. So this thing will move, but it'll also start spinning. So maybe by the time it's here, right, maybe it's rotated a little bit. So that's the idea, right? If you just give something a push, it will cause it to accelerate, but it will also cause it to, like in an angular sense, accelerate. So motion and rotation together. Okay, so conceptually I want that to be understood, but we're not going to do any problems like this with just a totally freely moving object that can move and rotate. One situation, though, is important enough, one special case is important enough that we need to talk about it, and that's rolling, when an object rolls. That's too important to skip. So let's talk about that, because that is an object. That object, when something rolls, it moves and it rotates together. But we're going to see in just a second, rolling is like special. The moving and the rotating are not totally independent. They kind of have to go together. We'll talk about that. All right, so first of all, obviously, things will roll if they are circular in cross-section. That could be like a disc, right, or it could be a sphere. Things that can roll. That can roll, if you slice them, you would see circles. Circular cross-section. Yeah, so here's the connection between the translational motion and the rotational motion that has to happen if you're rolling. So if you're rolling, and let's assume there's no slipping, it's not like skidding, like a tire skidding, like it's solidly on the surface that it's rolling on, and there's no slippage, right? So if you think about it, so when the object rotates one time, so let's take a point on this, say, disc or sphere or whatever, and as this thing rolls from here to here, this point is going to go around the circle, right? And let's say that that point has gone all the way around once in the time it took for this thing to roll from here to here, right? Maybe just to draw some like intermediate pictures, maybe here that point was like here, and then maybe here, the point was down at the bottom. And then it came, and then as this thing kept rolling, now it's rolling back up to here, right? So that one point kind of went down and then up. All right. Well, so that point, so basically, it's like, if imagine like cutting the circumference and laying it out. So from here to here has to equal the circumference, because that one point went all the way around. And so that's 2 pi times the radius. So when the object goes around once, the object will have moved 2 pi times its radius. That's the rolling. That's the connection between its rotating and its just regular moving. Now, put another way, the velocity is r times omega. So this is our old formula. V equals r times omega. That's the connection between regular speed and angular speed. And we have that here for the rolling, the situation where an object is rolling. So the velocity of the overall object, in other words, the center of mass velocity, is the radius of it times its angular velocity. One thing that is interesting is, so if I redraw the picture and I have the circle and it's rolling this way. If we think of a point on the outer edge up at the top, like I had pointed out over here. So this point is moving this way, right? Now, there's two parts to it though. It's moving to the right because the whole wheel is moving to the right, but also, just because this wheel is spinning this way, it also has a, some velocity that way because of that. And in fact, it's going double the speed. The point at the very top is going double the speed. Again, because it's got kind of two contributions to its speed. First, just the fact that the overall wheel is moving, but then secondly, that it's rotating. And so that even if this thing were just rotating in place, this guy would be moving pretty fast. But so it's both together actually give you double the speed. Now, a point at the bottom, it's got, again, because the wheel is moving this way at v, a speed v, but because this thing is rotating, it actually has, because of that, it has velocity going back the other way. And so actually, those cancel. And so the point at the bottom actually has velocity 0. Now that only lasts for a split second, for a moment, but that point is stationary just for a split second, because its rotational motion and its overall motion are kind of canceling out right at the bottom. And of course, that kind of has to be the case. The points that are touching the surface can't be moving, or else that would be slippage. That would be kinetic friction, right? And we're saying we don't have that when in our rolling. So the points right at the bottom have to be not moving when they're touching. Okay. Now a point right in the front, for example, that's moving. That has v going this way, but it also then would have downward motion. So it would be some diagonal. There would be a diagonal velocity that you could figure out. But the top and the bottom are kind of two interesting points. The top is moving at double the speed. The bottom is moving at 0 speed. Okay. So what I'd like to do in the case of rolling, we've talked about some of the ideas, but I'd also like to get an actual formula for the kinetic energy of a rolling object. So as we said, when an object can move and rotate, it's got two pieces of kinetic energy. It's got the translational and then it's got the rotational. So it's got 1/2 m and then just the v. VCM, again, this is just the v, like the speed at which it's rolling, not taking the spinning into account. Just like the speed that its center is rolling at. Plus, then we have the rotational, which we know is 1/2 I omega squared. Okay, so that's our formula for the kinetic energy, but we're going to do more. We're going to get this simplified a little bit. If I go back and remember this connection between v and omega, I can replace omega with v divided by r. So I would have 1/2 mvcm squared plus 1/2 I VCM squared over R squared. Okay, and then what I'm going to do is I'm going to factor out the common 1/2 on one side, and I'm going to factor out the common VCM squared. And that leaves the mass, but then it also leaves this other term, I over R squared. And so this is the overall kinetic energy of a rolling object. It's like 1/2 mv squared, our regular kinetic energy formula, but there's this, you have to add to the mass an additional term that just adds in the, what that is going to do is add in the rotating part of the energy. Okay. Okay, now I realize I never cut this video and stopped and started a new one, so this has been a long video. Let me just stop, and I'll just have a little bit more to finish off with, and we'll actually use this formula. So part 3 is coming up.